Welcome to our day 2 of the Introduction to Plant and Equipment Wellness Way. Day 1, we talked about the foundational concepts, the things that are the underlying approaches and intentions of plant wellness. Day 2, we're going to go into talking about how to apply these concepts in a structured process that we call the Plant and Equipment Wellness Way. So we're going to cover 6 bullet points, and it's all based around recognising risk, putting some sort of scale and size to the risk, and then if that risk is too big, we're going to put into place particular strategies to manage that risk. And we want to pick the strategies that are actually viable and the ones that work. And we'll see along the way how to begin measuring risk and how to track risk and how to be sure that when we choose to do something, there's a financial sense behind it. So let's move on. Probably an overview slide, just a conceptual slide of what the approach is in the methodology. Just wanted to have one big picture or one clear picture of what we're trying to do here. We're going to begin with the process maps of the situation. And that situation might be a production process, might be a work procedure. We're going to turn everything into a flow chart, boxes and arrows that explain how we start at one end and get to the outcome at the other end. Along the way, because now everything's broken down into its individual activities and individual steps in that process, we can begin looking at what risks are in each step and giving it some sort of grade of chance of success in each of these steps to get the complete process working properly. So from understanding the size of the risk, we're going to look at putting in risk controls. Now, what do we have to do proactively to prevent the problem? Sure, we can fix it when it breaks. That's breakdown maintenance, that's repairs, but that isn't what we want. That's meaning our process has failed. So we want to build a process where the risk is discovered, minimised, and the problem's prevented in the first place as part of the process of doing that work. So from that risk control, we're going to break into a number of options, and perhaps all of them together is required. One will be an operational focus. One will be an engineering and design focus, because we know from the life cycle requirements that the design is wrong, everything else goes wrong later on. Then of course there'll be a maintenance focus as well. So we have 3 opportunities and 3 ways of minimising risk, and we might just choose to use one or choose to use all 3. That's the whole point of analysing the situation in detail, so we can make the smart choices to minimise the risks for that whole process. Once we go down each of these legs, they have their own particular requirements that each leg makes clear we have to adopt. And in the end, we come down to documented ways of doing the process, the activity, the work that include the controls. And it'll be written up as a 3T, Accuracy Controlled Enterprise 3T document. So we'll be stepping through, basically writing a document of exactly how to do this right. I relate it very much to a movie. When you go to the movie, you watch the scenes, you watch the whole episode play out. When you think back to what they did to get this movie that you're looking at and everything's so seamless, everything works as scripted, somebody must have written that script, must have rewritten it, played it a couple of times, rewritten it, got some feedback from people till eventually this script that we are now watching as a movie works beautifully. There's nothing gone wrong, everything works as the director wants. So the same concept with our documentation of managing a process. Please tell me exactly what the right thing to do is in this job. Please tell me exactly how to run this machine perfectly right. Please tell me exactly how to make this product from raw materials into a saleable item that our customers love to have. Teach me the right way. And like a movie, we're going to write and rewrite and practice and script it and learn it and play it again if we have to until we get this final product that is exactly how to make what we want to do happen. So everything comes down to writing a document, and that document contains the correct way to achieve the results we're after, and then we train people to do that. And we measure ourselves along the way. The 3 T's is to have regular tests along the way to prove we're actually doing what we're meant to be doing. So at the end, we guarantee the right outcome because the whole thing is written exactly the way it's meant to be. Boeing have got it right. Now, the aircraft industry guys are 20, 30 years ahead of us. We should be following them their leadership, because what they've been doing and what they've been learning and putting into their documentation and controlling their construction process and maintenance process of aircraft is exactly the right thing to do. So I'm simply going to say, look, follow their lead, detail the information, train people up to do it properly, and then apply that known process correctly. So yeah, we will have a solution to adopt, and we're going to then measure how effective that solution is.
Are the 6 steps basically embedded in there?
That will get us through this entire slide. That's the whole point of the 6 steps, to come out at the end with a process I can give to anybody in the world and say, follow these 6 steps. Out of those 6 steps we apply, we're going to fit somewhere on this slide at various points, right down to measuring how well we're doing this process. Can we find some shortcuts, some smarter solutions, and continually improving as we learn more things. So yeah, really the methodology is very much explained in that. How to get through that is the 6 steps we're going to be looking at today. So the first thing, of course, is finding out, is there a risk? Because sometimes there's a risk, but nobody cares. You're going to drive a car on the road. You'll drive a car all your life. I can guarantee today there are going to be dozens of accidents and many deaths, but you and I will drive a car anyway. So if the risk is unimportant, if the risk is something we're willing to wear, then we're not going to waste any more time on minimising that risk, because it's pointless. We're willing to accept the chance that we might die for the benefit of having a vehicle to drive around, knowing that the odds may come against us one day. So we want to find out where the risks are, grade the risks, and the ones that we don't want to live with, we will then do something about. So we need a way of achieving that outcome, a way of understanding where the risks lie. And the way that we're going to adopt is literally a flowchart methodology. From the beginning of what we're looking at through to the end, we're going to break it down into, I call them process maps, because it's a map of the whole process, but it's purely a technique to let us break it down to step-by-step aspects of this whole process. The risk in each step, and to identify the risk, we're going to go back to our physics of failure listing and actually say, what if there's a fire? What if there's a high vibration? What if it's been miscorrectly assembled? And actually say, if these things can possibly happen along this process, is it important if they do or if they don't? If it's important that they don't happen, then we're going to say, what are we going to do about that? And then we start building the solutions into our procedure. So we're going to categorise the risk. This again is a typical process for risk management. What's the cost of something going wrong? What's the cost of downtime, health and safety? If it ends up hurting somebody, well, we can't accept that. If it slows production down too much, we can't accept that. If it ends up, this risk causes us to make scrap product that I have to throw away or rework, then I'm losing money. And I could have stopped that by understanding, hey, I can design a process to prevent that problem in the first place. So we want to understand what the impact of that risk is. If the impact is acceptable, we live with it. If it's unacceptable, we do something about it. So from all that, we come down to working out what's the cost of living with this risk. And if the cost is $10 million and we can't afford to have that risk happen, then we build solutions to prevent it in the first place. Fundamentally, the understanding that we're looking for is a realisation that our whole world is series activities or series processes. A business life cycle is a series process. I get it wrong here and everything after that ends up being a nightmare. Our activities at work, that's a series process. And there's not many jobs that are only 5 tasks long. Maintenance work, you're talking 20, 25, 50 tasks. And this chain is a long, long chain, and every single item has to go right. Perhaps, maybe it doesn't matter. We'll have to see. If it doesn't matter if task 4 goes wrong or not done properly to the whole job, then we just don't worry about task 4. Just let the dice roll, and whatever comes up, we accept. Same with our manufacturing or any business. There are processes, and there are other processes that impact on those processes. And so we have this hodgepodge of high-risk scenarios. And of course our machines, they're all series components assembled together to make a machine that works as a complete unit. So everywhere we have opportunities for something to go wrong. So I want to break these all down into identifiable places where those opportunities arise. So some thoughts that I put together there, without the tools to find exactly what they need to focus on, without evidence that high reliability is worthwhile, and without an achievable plan to deliver it, organisations will waste away. So if we want to have an organisation that is robust, that is looking to change, that is looking forward to change in a better way, then understanding what prevents them from doing it becomes important. And then those things that stop the company from moving forward, we have to proactively address those. Now, risk is an interesting concept. When you sort of look at what risk is, it's this equation up here. There are three components. There's the consequential cost of loss when something goes bad. When the machine breaks down, there will be money lost. The frequency of opportunity for failure is another factor in risk, because if opportunity is very, very low, then the odds of something happening fall away. It's unlikely to occur. Yesterday, our lubrication management, we saw when the oil is contaminated heavily with wear particles, many failures. When I clean that wear particles out and get down to very few in a drop of oil, that failure rate comes right down to fractions of the previous failure rate. So the opportunity is an important thing to understanding risk. If I can reduce opportunity, then I will reduce the risk. The other component is chance. The fact that opportunity is there is one thing. The fact that I got 150,000 wear particles in my drop of oil is a chance, is something that is an opportunity for them to go wrong. The chance the particle will get between the teeth of the gears, now that's something totally different. So I could have wear particles, but they may not actually get between the gear teeth or between the bearings. So though it's contamination in the oil, it doesn't mean it will naturally lead to a bearing failure. The opportunity's always there. The fact the particle will not yet get into the bearing, that's a chance issue. So I can have dirty oil and have the machine never fail because the chance never occurs. But the point is, with lots of dirty oil, the opportunity is always there for it to go wrong. And of course, with enough time and enough situational circumstances, the risk eventually comes our way. So we have the three components of risk. We typically consider the chance and the consequence. Within that chance also includes the opportunity aspect of it. Now, risk is what they call is scale-free. Scale-free means one situation can lead to a very small problem, and the same situation can lead to massive disaster. For example, if I had an electric motor and the internal windings have a bus bar problem, or have a bar problem, a winding problem, now that problem can either just lead to that electric motor failing and it breaks, the equipment stops, or if I'm particularly unlucky, that same problem can lead to a fire in the electric motor that now burns down the whole building, and all from the very same initial situation. So that's what scale-free means. That same risk can lead to negligible problems, or it can lead to a total disaster. And no one knows what's going to happen because it depends on the circumstances of that event. It's also driven by a few key factors. We don't have to necessarily solve all the world's problems to stop a risk scenario. We've got to find out what are the key factors that lead to the risk and control those key factors. And so maybe out of all the things that can go wrong, the most likely ones are 2 or 3 possibilities. So we want to find those 2 or 3 possibilities. We also know that risk indicates the presence of the interaction of uncoordinated agents. When things are uncoordinated and many random situations are occurring all the time, all around you, these random events begin to line up from time to time into hazards and into consequences of these situations. So risk reflects the uncertainty, the randomness of what's going on around us all the time. Because sometimes those Swiss cheese holes, they line up, and they line up when they want to, whenever the situation arises. And suddenly it reflects that his decision 10 years ago, my decision yesterday, and the supervisor's decision this morning, suddenly the 3 decisions over that time period line up in a bad way. And now those choices lead to a failure. And that's the bit that we're trying to prevent. Interestingly, risk events are more likely than by pure chance. We have more trouble from risk situations than we do from pure chance situations. And I think the reason is because opportunity is always there, whereas chance just happens by itself. I roll the dice and what number comes up is pure chance. But when I have a working situation in a company, that chance is randomly happening because it's uncoordinated agents working around all the time. And because opportunity is continually there, risk ends up having more disasters than a chance situation would lead to. So your risk is an interesting factor because we don't understand how that arises, how opportunity and chance interact. We never actually see why things are occurring and how to minimise that opportunity and that likelihood over time. In the end, as a business, as an organisation, there isn't a lot of things we can do. Certainly when it comes to maintenance of machines to prevent breakdowns and to minimise risk, there's only a few strategies we've actually got available. Preventative maintenance, corrective maintenance. So we detect something is not right, and if we don't correct it, will lead to a failure. So we actually stop the machine and correct the problem. Run to failure maintenance. So we'll accept a breakdown and simply repair it when it breaks. This you might use if you have a standby unit. You've got a standby, let the duty unit fail, start the standby and repair the duty unit on a breakdown basis. Design out the problem. Now, if the issue is poor material selection, if the issue is poor process control, then let's re-engineer that and solve that problem once and for all. PDM is predictive maintenance. So condition monitoring is going to be used to monitor the evidence of something going wrong. Because if I can detect the P point early before it becomes a disaster, then I can do planned maintenance at lower cost. And PRM is precision maintenance. This, of course, is all about minimising the stress in the parts that make up the machine. And if I can minimise my stress right down low, then I'm going to naturally increase the service life of those parts. So yeah, when it comes to maintenance strategies, there isn't that many choices, and we're going to play with our options and pick the right ones to match the risk. And we want to have a technique to achieve that. Again, from yesterday, we mentioned that the chance of failure is the opposite of reliability. Reliability is the chance of success. Chance of failure is 1 times minus the chance of success. So reliability and risk, they go like this. And if I can minimise the risk, I naturally lift reliability. And if I can increase reliability, I naturally drive the risk down as well. They're inversely proportional. Over the years, I guess from the mid-1980s in particular, it became clear to companies that asset management and the control of how their assets operate, to get maximum profitability out of those, was an important factor. From my reading, DuPont here in the USA was one of the big starters of good asset management practice. And if you do research, you very quickly come across a lot of information from the DuPont days, from those early days when they began finding better answers. And one of the things that DuPont used as an explanation of why bother doing asset management well, why bother running a plant well, why bother doing maintenance well, was that their company was actually a bucket for collecting problems. So their model is called the Defect Creation and Failure Initiation model. So I want to explain what they meant by that, and in particular where this takes us in our thinking of how to create reliability. What DuPont found was their company was collecting trouble from everywhere, from operating issues, fabricators' problems, design errors from engineers. We saw yesterday the nuclear power industry, 35% of the early life problems are design problems. Installation problems from wrongly installed equipment, decisions from managers, not seeing the full picture of things, and of course workmanship errors, human error type factors. And that wasn't just in maintenance, it goes across the business. IT, accounting, finance, everybody has humans in their process and humans create human error. So what DuPont had done unintentionally or without understanding the consequences, they began saying, well look, these problems are now in our company, we must fix these problems. So they had a big maintenance department, and of course across the whole company the same story. A big IT group, a big accounting group, and all because they were thinking, well, we've got to solve it. Here, it's our issue now, we've got to solve it. They questioned that. They said, well, why are we doing that? Because if we could actually do this, if we could actually go out and stop these problems, stop these defects, stop the issues that are causing our machine failures from coming into us in the first place, then I need a smaller maintenance crew. I need a smaller IT group, a smaller finance group. And they did that. That's how they took their strategy. They ended up writing 105 documents on how to run their business from procurement right through to maintenance. And they made it very clear, this is how we will do our business, and any suppliers, you will follow our requirements. They actually began doing drawings of how to assemble pump sets, how to fabricators to make the product that they wanted to meet certain standards. So in doing that, over the years that they applied this, they began to drive their costs down and improve their availability. So the concept worked, and it's a smart, and you can see the sense of that. Well, why are we living with mistakes that someone else made and now I've got to fix and I've got to pay for? It's going to cost me an absolute fortune because of their mistake. So the idea of minimising error, at the very beginning, very successful concept, very important concept. Now, I want to talk a little bit about the trap that is very easy to fall into. This here is a soft foot problem, and a soft foot literally is, let me give you an example. Let me grab this chair. Bit of cracks with soft foot problem. That's okay, I've got this thing here. Okay, soft foot. Now, if I have that soft foot problem on a new machine and I don't do anything about it, simply install the machine on its base and then bolt that machine down without removing the soft foot, I'm going to cause a banana of that machine body, and all the parts and bearings and shafts and components inside, they're going to be under stress. They're going to be distorted, and that's a brand new machine. Brand new machine with a soft foot problem. Internally, my parts are already under high stress and the machine hasn't even been used yet. And if I use the machine when the parts are under high stress and they're banana shaped or they're squashed together very hard, they're not going to last very long. You know, press the button, the machine will go. It'll just fail in a matter of months when it should have been many, many years trouble-free operation. So if I have soft foot, I can solve it. I solve soft foot by putting a shim. Put a shim there, problem gone away. So yeah, we can fix that problem. Soft foot is something that certainly is solvable. The hassle is we then give ourselves a reliability problem for the remaining life of this equipment. What I've done here, this is our foot, our machine foot that's part of our assembled machine. If it was perfect, if that base plate was perfectly flat and the feet were perfectly sitting on that machine, as we can make that level of accuracy, this holding down process, this holding down system would involve the bolt head, the machine foot itself, the shank going through, some sort of threading connection on the frame itself, and then of course the frame. There'd be a 5-step holding down process. But of course we've got a soft foot problem. So I shim up the soft foot. Soft foot problem goes away, the machine is now not being deformed. But I now have got a 10-step holding down process. This person's put in 5 shims. I have got 5 more things to go wrong in the future of this company. So this brand new machine that will be there now for 50 years or 25 years, whatever the case is, I have given ourselves 5 more opportunities for this to go wrong at any point in time. So whenever this machine's maintained by my guys, whenever we take that machine out of place to do some sort of maintenance, if the guys only put back 4 shims, because the technician thinks, well, I pulled shims out, I put shims in. So up here in his mind, it's okay, he's put shims back where they belonged. But if one falls in the dirt or one's lost somewhere and nobody replaces it, now 4 shims go back. In their mind, it's all okay because shims came out, shims go back in, except now I've got a soft foot problem that no one's recognised because nobody's thought it could happen. And so, yes, we can fix defects, but in fixing defects, we give ourselves years of trouble. Forevermore, we'll have trouble. Now, I'm 56. When I was 54, I learnt something. It turns out that when you start putting shims together, when you start putting a stack of shims together, especially when you put a stack of 5 shims together, when I've got a stack of shims, I've got many faces. And at each face, over time, that face relaxes. And so that initial tension I had on there, in the next few weeks, next few months, that tension relaxes right off because the faces, the surface of each face, slackens and the tension disappears. So in a matter of weeks, this fastened up hold-down bolt will actually be loose because I've got too many shims in here. And each shim face becomes a place to reduce that tension. So if I'm going to start using shims, I've got to ask the question. 5 shims is too much. 5 shims means I will create a loose connection in about the next few weeks. It'll start to go loose because the metallic nature of our shim material will the spring basically slackens off. So 5 shims are too many. How many is acceptable? So this particular presentation, we discussed that, and the group began to talk about what they do in their companies. The perfect solution, if you're going to have a shim, then 1 shim is perfect. That's the best we can achieve if we're going to have a shim. But that means you have to get a perfectly sized shim, which is very unlikely in most general situations. So now 2 becomes a possibility because with 2 I can play with the size of the shims that I can use. That, from what the guys were telling me in the conversation, is also a hard thing to get right on a regular basis. So eventually we settled on 3 as the maximum number of shims to use to not have as big a problem with slackening of faces, but it doesn't actually prevent the reliability issues in the years to come. So yeah, we can solve our problems, but we don't then increase reliability. We actually decrease reliability of the equipment. Now, the other issue too is sometimes you see the guys put a number of washers underneath bolt heads and you start to make up the gap, to fill up, to make up the space. They'll put a number of washers, same story. When you start putting multiple washers, you've got multiple faces. So you must eventually have a loose connection. So if you're going to start using shims, to protect against loose connections that you will surely have because the process you've chosen must lead to loose fasteners, you've got to add 1 more process on top of that. On a regular basis across your whole company, you'll have to go and tighten up every hold-down bolt to make sure that ones with shims have not slackened off. So if I start using shims, I'm going to then add in a regular tightening process of every bolt that has a shim under it. Otherwise, in time, these hold-down bolts will come loose. The machine starts vibrating, it gets bigger and bigger, and the bearings inside start being knocked about, and I have a breakdown. So yeah, this is the worry with accepting defects. And the whole issue is we can make a flat base plate. We can make base plates so flat that we don't need any shims at all. But we have to get our manufacturers to do that for us. And that's the bit we're going to have to make sure that they understand what trouble they're causing us. When I buy a new pump in, it's already shimmed up at their workshop, they have given me breakdowns. They've given me a breakdown every now and again for the next 50 years this machine's in service. And they don't see it. And I never saw it until 2 years ago. So it's interesting when you look at the limitations of our materials and what that means in terms of the longevity of our plant.
You know, I just thought it was interesting that if you look at your house, carpenters are master uses of shims. Every footer that goes up to support your frame, some have a shim under it, but some don't. Some have 3 shims. It's a mishmash.
We've done this because when something's happened and something's gone wrong, I've got to have an answer. I've got to solve this in some way. So we solve it. We will solve our defects, we'll solve our problems, have done for 10,000 years, and we'll do for another 10,000. But the point is you have now got more things to go wrong. And every now and again, the risk situation might arise when that unlucky day it happens to us. And it didn't have to happen, but the opportunity is now there that had it been right, there'd be no opportunity to go wrong. But now I've got opportunities in 5 more places, and they are there forevermore, and the day might come against us one time. So we just never know. That's risk, The risk is there. Whether it actually turns into a disaster, never know. May never happen, but the opportunity is there for it to happen. I want to talk a little bit about how engineers get caught out when they specify equipment. This is the International Tolerance Grade Table. The IT5 we saw yesterday was And they use this table to tolerance the components of the parts they make. It's a standard practice, it's a universal convention. I came across a paper written by somebody comparing ANSI pump base plate flatness with the API 610. API 610 pump, centrifugal pump, is an oil and gas pump. It's the oil and gas standard they require for centrifugal pumps. API, the ANSI, American National Standards Institute pump standard, is for centrifugal pumps. Each one has a different quality requirements. And this guy was comparing the ANSI pump flatness allowance with the API 610 flatness allowance. So I thought, let me show that on the IT table as to represent what that actually means in terms of the difference between the two. The ANSI pump base says they will accept up to a 5 thou unflatness per foot. Now 5 thou unflatness per foot is a really bad soft foot problem. That's a terrible. Now this is saying until you're past 5 thou unflatness per foot, don't worry about solving solving a soft foot problem. Don't bother shimming it up. Just that's okay to accept. Well, if I buy that pump and it is at the extreme end of that distribution, then I have brought in breakdowns for this company forevermore. And the supplier sold that to me, and I paid in good money to do that. That's the standard. That standard says that's okay, and take it as it comes. Oil and gas guys have gone a step further and said, well, that's not good enough for us. We want to get something that's more certain of good reliability. In their requirements, in the API 610 for base plate flatness, they will accept nothing more than 2 thou per foot. Now, I'm a fitter machinist. I used to machine base plates, and I know that 2 thou per foot is not a big stretch. It's much better than 5 thou per foot, but it's not a big stretch. It's still a soft foot issue there. Now, of course, what they're counting on is the distribution. When they manufacture these machines and these base plates, there will be a distribution. What these manufacturers, or what these standards counting on, is that the plus or minus 1 to 2 sigma is going to get most of the manufacturing output. The unlucky guys that get the worst case outlers and down here which will lead to problems, won't be too many of those. So in a company that makes 1,000 of these pumps, maybe 4 or 5 are going to be at the extreme end. So most guys are going to buy pumps, so they're going to be sort of acceptable. So the worry is you won't know which one of these positions you are on the distribution. You just buy a pump thinking it will be okay. So your 2 thou per foot certainly is far, far better, but we can do better again. So I ended up overlaying the two, the ANSI and the API, on the international tolerance grade number, because an IT11 and IT10 is very poor manufacturing specs, disastrous manufacturing specs as a matter of fact. Then at IT7, IT8, we're getting down to reasonable general engineering requirements. So down here we're getting to finer quality work. But even that's not good enough, because I know we can do better than that. So I said, well, the manufacturer of bearings requires to have an IT5 as their worst case scenario to get a proper service life out of that bearing. So I thought, well, what does an IT5 look like when it comes to base plate flatness? So I put this circle around the IT5, and it talks about 40 microns per metre. So at that level there, you don't need shims. Now, you've got a machine that is now in a position where everything is where it should be without using shims. So I said to companies, look, challenge your suppliers to deliver IT5 quality, because an IT10 quality isn't going to cut it for your success. An IT7 is better, but nowhere near as well as you can be. Shoot for excellence. Shoot for excellence, because it will pay back a fortune for you very, very easily. Different topic now, about cost. Yesterday we saw this financial model of a business, how we got fixed costs and variable costs, and the two add up to be a total cost. And we introduced a breakdown to this business. And we had to, and I mentioned the cost of a breakdown is the total cost the business suffers. I can repair a breakdown and have a maintenance cost for that repair, a direct maintenance cost. Materials, labour, supervision, So I can cost that as a maintenance value quite easily. What I can't cost is everything else the company lost or paid for that there is no value to show. That's the value we have to use in our risk costing assessment. And I call that value the defect and failure true cost or defect and failure total cost. I don't mind what you call it. I left the acronym DaFT on purpose because we can drop the A and call it DFT cost so nobody's offended, but I thought, gee, it is daft. It is daft to live in a company where you don't understand the cost of a breakdown to your business. So left it as daft costs. Some guys don't like it because daft implies that we're not managing properly. Yes, we're not managing properly, but you call it what you want to call it. The whole point is it's all the costs the company will lose that we want to know when we start measuring the risk to the business. So I sat down and began writing what sort of costs can a company lose in a breakdown. There are, I think, 65 different costs. Now, not all 65 will happen in every single breakdown. Now, there'll be costs for additional labour, unnecessary overtime. There'll be waste of product, perhaps some scrapping. There could be some reprocessing. When it comes to additional services, I have to get a subcontractor in or get a contract welder to come back on site. I've got to pay subcontractors, pay their travelling. I have to pay for consultants. And you know, these costs arise because once the machine's broken down, I've got to get it working. I've got no choice. And I'll pay whatever I've got to pay to get the machine back in service. And there'll be materials costs, there'll be equipment costs. There'll be, if the machine process is a hot process, I've got to cool that whole machine down, then all the energy that was in the machine, I've just lost the energy. Had to take a hot process down to cool conditions to be able to work on it. Then I've got to reheat the whole thing up again on restart. So I'm going to lose energy to reheat the machine. That energy has to be paid for, and of course the company pays for that. Does that cost of reheating the machine appear in the cost of the breakdown? Most companies wouldn't even think about it. Yet the business will pay for that without question. Over here, consequential costs. In our business we lost because we couldn't sell the product we could have made in the time that it was broken down. Or penalty fees from clients because we've now affected their business and they're going to penalise us for their losses. There's an interesting one here, administration. Now my invoice matching people are on the breakdown. Over here, an administration person, so 1 month after the breakdown, all the invoices come in from the contractors and from the suppliers of the parts. So now 1 month after the breakdown's been addressed, the people in accounts are working on the breakdown because they've got the invoice, got to match purchase orders against the invoice, got to pay the invoice, all because the breakdown happened. So the truth is, companies, when we have a breakdown, every department has an effect. If I've got to ring the client and say, look, Mr. Client, I'm sorry, I've got a breakdown in the plant, you're going to be 2 days late with your product. Now my sales guy is on the breakdown. And my client now knows that we have unreliable plant. They had to ring up and say, we can't meet the order that we promised we'd give you some months ago. So we have to recognise as a business, there's a huge cost surge from failure. Failure is terribly expensive. This is where yesterday I mentioned a ratio of between 7 and 15 times the direct maintenance cost. If I can find a ratio, because direct maintenance cost is easy to calculate. What I can't calculate is everything else that I have no value for, but the company will pay for. So I wanted to get some sort of ratio, and I came down to 1 in 10 times. That's typically fair enough for process plants. Batch plants are a little bit different. Batch plants, because they are a localised issue, the knock-on effect normally isn't so much. With a batch plant, I normally say about 5, about half the process plant cost. Now that was from my testing of this in one of the companies I worked at. What I actually did was develop some spreadsheets with those 65 costs in a spreadsheet. And I went and picked a couple of breakdowns, historic breakdowns, and I went back through that breakdown and analysed that to death. You know, every single cost that breakdown caused the company, right down to the meetings in the meeting room amongst supervision to discuss how to repair that problem. Pick up every single cent, because the company will pay for it all. What we don't see, and what accountants in the company don't see, and what the CEO doesn't see, is the other costs that the company's forking out, but just don't have a value for. So I want to find all those costs, because that's what the risk is to the business, losing all that money. Not just maintenance repair, not just the downtime and product they couldn't make, but everything that flows across the whole business for the coming months after the breakdown. Very onerous process. There is no software out there that does this for us. I think a progression for industry will be to actually begin pricing the true total cost of their breakdowns. That'll be a huge progression because nothing can be hidden then. The real cost will come in everybody's face and it'll scare them to death. That's why I'm so sure when it comes to plant and equipment wellness, there's big dollars in our concepts, absolute fortunes, because nobody sees how much money falls off the table or is left in the pile that could have been gotten hold of so easily if they could see where it was.
Why do you think management hasn't been willing to look at these costs? I mean, it's not like they're invisible, but they just have ignored them.
What I find, if companies are meeting budget, everybody's happy. Now, as long as you are achieving the target, if you were set to hit a budget, why rock the boat? Why go out and make more work for yourself and cause more trouble for someone else? So yeah, once companies are happy in this little world of, oh, we're meeting budget, we're meeting target, there's no drive, there's no incentive to look for anything else. What they miss, of course, is there is value in looking for that.
What I've also discovered is they set their budgets based on covering these costs. They accept this risk
Yes.
because it's always happened.
Yeah.
So to get, to get outside, because many times I've asked, well, how do you set your annual business plan when I'm talking to them about, especially maintenance or engineering budgets,
Yes.
and they use historic data to set their next year's AVP. And
Exactly.
I've
Yes.
discovered that. So this is hidden from them.
Yeah, exactly. No one's showed them. No one's actually showed them where their money is going. Right. It's just a bucket of money is given to them, and that bucket's big enough to cover all the hassle and problems they're actually accepting.
Exactly. They accept it.
But then when you say, well, there may be more to this picture, do they just not want to hear it?
Well, one of the reasons I'm here is I want to learn how to show it to them better. There's two things. One is you have to show them the picture clear enough so they're willing to make the leap of faith and go down the reliability path. The second is, based on my own experience, you have to be prepared to lead them once they make the leap of faith.
Yes.
I've had trouble in both avenues. When I've gotten them to make the leap of faith, I haven't been well enough prepared to lead them.
Yes. And you need to have believable evidence. You can't make this up. It has to be real. The fact they haven't seen it themselves, that's one issue. But now you've shown it, this is what it really is, and here's why I know that's right, because I've got your data and I've looked at your breakdowns and I've gone and talked to your people, and here's the full story of what's really happening in your business. So yeah, a lot of this stuff we're discussing is how to make the invisible visible to those that haven't got eyes to see it in the first place.
Is this a real critical point for PEW? It's a sticking point that you have to overcome, or the rest of it doesn't work so well.
That's why I wanted to get this ratio. I wanted to get a ratio of direct maintenance cost, because that's the easy one, unquestionable, out of their computer system, their numbers. If I can get a ratio that represents the full business loss, then I just multiply that by 10 and say, that $10,000 job in direct maintenance cost wasn't $10,000 that cost you. It cost you $100,000, possibly $100,050. Is that okay with you? Are you willing to carry that risk? So yeah, and what we typically would do in a company, we would go and get 3 or 4 of their breakdowns and go and analyse their business in their situation and come back with these spreadsheets for their business and say, Mr. Manager, Mr. CEO, here's what's happening. Here's what's really happening. And of course, out of that, there'd be a big pile of money sitting there, shining gold that they can get. But they've got to change their ways. Remember, they are where they are today because of the past practices and processes that are adopted. Their result today is a process outcome of what they're doing. I've got to change the process. If I want to get that gold back into my pocket, I've got to get a process that brings the gold that's now falling off the table into my vault. And what they're now doing won't do it. If it could, they'd be doing it. But it can't. They've got to change. They've got to see, and is the change worthwhile? How much money will it cost to make the change? How much will I get back from that change? And unless it's a business case, neither you nor the CEO anywhere in the world would accept a change. It has to be money, and guaranteed money, certain money without question. I wouldn't want to take a business down a path that's going to cost a lot of money and uncertainty without knowing at the end this investment will pay back. So PEW is all about building a really powerful business case very early on before we start making the changes, proving that this is wrong, this is not paying off, you're losing so much money. You do these changes, here's the risk, here's the number of risks. We address these risks in this way. Because the risks are now removed, I can guarantee with you, if you do what we suggest from our analysis, you will produce this much extra profit.
Do you think this would apply also to a service business that did not have equipment, heavy equipment?
The principles would certainly do that. Yeah, it's not about machinery, it's about where the money flow is in the company. Wherever the money flow is, we're going to monitor the money flow, we're going to gauge what's happening with that money. If it's a wasted money, we're going to pick it up and say, well, this is waste and we can save that by 50%.
For example, there's a huge business in this country of connected with medical insurance claims, people just entering information. And it's estimated that 3 to 5% of all those entries are defective.
Easy.
And so that means these people, these 3 to 5% have improper information in their medical records.
Could be dangerous.
And you don't know who the 3 to 5% are. So, you know, there are consequences all the way downstream.
All their life, yeah, absolutely. Look, to me, they're universal principles. If you can turn something into a process, boxes and arrows on a piece of paper, this will work. So what that process represents, not important. In fact, there we go. There's the whole idea. Let's start with a process map. In this particular case, we have our power supply from a switchboard, and there's a power cable running to an electric motor that drives a coupling through the bearing housings of the wet end to a wet end of a pump. So this is a pump set with a power supply. And that's all it's meant to be. And then, of course, I say, well, the power supply box, what's the process in that box? And so I break it out again. Electric motor, what's the process in the electric motor? So I break it out again. So I can keep pulling things apart right down eventually to the individual part numbers if I want to go that far. Now, of course, once I've got that layout, I can say, if the brushes fail, what's the impact? Does that matter if the brushes fail on this motor, on this pump, to this company? If the answer is no, I don't care if the brushes fail. We've got a standby unit. Great. I'm not going to do much work on that one there. But if this is the only motor they've got and the only pump they've got and the only process that makes money in the business, vital stuff to know. Hey, I've got to make sure we have no brush failures. I've got to make sure I have no stator failures. You know? So this makes very clear, where are the risks to this company in this situation today? And can we live with those? And if we can live with those, great, live with them. If you can't live with them, what are you doing about it? Let's design a process to ensure that they do not get caught out. And so PW is, everything hangs off this analysis. So I've got to talk about what can fail brushes, what can fail rotors. And a rotor in a motor, dozens of ways to fail. Now, will all those dozens of ways happen in this motor, in this company? Probably not. Maybe only half a dozen of those dozens of ways. Or it could be a dozen of the dozens of ways. I don't know. The analysis is to understand this company, the way we operate, the way we maintain, the supplier of our equipment, the way they design that item. What's the risks of all those things coming together in an unknown way on a rotten day and the luck goes against us? So I'm being a bit pessimistic here. I'm going to start with the worst case scenario because the worst case scenario could happen. Probably won't. It's unlikely to have real bad things happen, but every now and again they do. So I want to understand how bad it could be if it's the worst case, and then from the worst case begin putting in the right techniques and methods and strategies and procedures to take that risk lower and lower and lower. Then as I build this documentation up, which is the scripted way to run the movie, and this is going to be written up how exactly to run this machine and run this process to have very few problems, then that's the script, guys. This is what we've got to learn and practice and become very good at doing and delivering. And to me, it's very much like making a movie. It isn't much harder than that in this concept. So yeah, for each of those previous boxes, we look at the life cycle issues. Across here, this is meant to be a list of all the possible ways a stress can occur in a component. Not every single one will apply in every single case, but we want to use a checklist. I don't want to have a team of guys brainstorming what can go wrong with a rotor. because any team of guys will only have a limited experience across their life of what can cause rotors to fail. I want to have all possible reasons a rotor can fail and be aware of those and say, will it apply or will it not? So this table was all about what possible ways can the microstructure be failed in this rotor, in this bearing, in this gear. Will these occur in this company? Is it an issue? If it's not an issue, forget it. Don't need it, don't need it, don't need it. Eventually, I'm going to build up a spreadsheet of all the things that could impact this particular part in this machine, in this plant. And then I'm going to start saying, well, which of these can't we accept? What risk of these can't we allow these to happen? Then I start building up the solutions in the script we build for the future of this item of equipment. So yeah, it applies to electronics. You know, it doesn't matter. We're trying to find where the stress will come from, because these parts, this microstructure doesn't care the reason for the stress. You know, it just sees the stress. It'll just see a stress and it'll damage you. It doesn't know that I'm rolling up. It just sees a stress. It just fails. So I'm worried about where the stress comes from, because it's the stress that kills it. And the stress can come from dozens of places, and a team of guys won't find them all. They'll find, maybe they might find half. Now that might be okay. It depends how big might is. If you can't afford that machine to fail and they've only picked up half the possible problems, then there's another half out there, another dozen or so out there that are sitting around waiting. And risk is always there. Opportunity arises, and that risk and that chance on that day. So I'm being pessimistic on purpose, looking for the worst case.
You know, in my experience, that's the way most of these failure mode and effects analysis take place. It's just brainstorming, frequently by people on a team who don't even know how the thing works. They just think, well, maybe this could happen.
Look, to me, they're good. It's worth doing that. It's a place to start. As long as you understand it isn't the place to end. Okay, the team has value. The guys do know things, and guys know things that other guys don't know. We want to pull that out of people. So yeah, that's a useful tool, but it isn't the only tool, nor is it necessarily far enough. But the thing is to recognise that we have to go a step further. So in the end, we're going to build a table. It ends up being a documented process. So I'm going to have my asset down by its assemblies, by necessarily perhaps even its parts. Each of these parts will have its different possible causes of failure from that list and from the brainstorming. I don't mind. I'm just looking for stress. Whatever can cause a stress, I've got to find that cause. And on we go. So what is the effect of that event if it happens? Worst, if that bearing in this motor fails, what's the effect on the motor, on the process, and of course on the company? So in the end, I want to work out what's the defect and failure total cost. What will this company lose globally if this happens? Because that's serious money. That's the money I've got to talk to managers with. Maintenance cost, I can't talk about that. It's peanuts. It's the money that they don't see being lost. I've got to show them. So yeah, they will have a spreadsheet. I can't see any other way to simplify that. It ends up being obviously could be a very long spreadsheet, but the whole point is we don't want to hide anything that's important to know. Now that applies to when it comes to work activities. This 12-step job, each of these tasks, it's a series process. Does it matter if this tightening of a fastener goes wrong? Does it matter if you've got a loose fastener or an over-tight fastener? If it doesn't matter, just let the guy use his muscles. If it matters, that fastener has to be right. Can't use muscles. Muscles has too much distribution. I've got to go to a better solution because the risk of failure here is so expensive. So the same concept, it's just a process. It's just boxes and arrows. Box by box, I can find out what possible risks are there. And if they're not acceptable, I want to design a solution right now, not wait to see if the dice roll the right way or the wrong way for us. And that'll come again down to some sort of table. It'll be task by task, risk by risk. And again, this might be one guy working alone. One benefit of having this approach is this table can be filled out by one person. One person who knows the job can fill this table out as the first cut pass. Same with this table here for equipment. This can be done by one person that knows the machinery, knows the engineering. That won't be enough. to accept their outcomes, because I need to have another person that's knowledgeable in that particular process or that particular job to also look at that. But I have got here a way of minimising my resources that are drawn into the analysis. One guy that knows what they're doing does this analysis first. Then another person who's later on in the process, so a couple of days later, a couple of weeks later, it doesn't really matter, comes in with a fresh pair of eyes and reviews what this first person does. So as opposed to like RCM, reliability-centered maintenance, or a brainstorming, I don't bring the whole team together initially. I bring a competent person to get to the analysis first. He does the first cut pass, and someone else that's also competent reviews that work. So now I've got two independent people, parallel activities, that hopefully will give us a good outcome in the end.
Do you think some companies would be, managers would be resistant to do this because they don't want to know the answer? Somebody might say, well, why did it take you this long to figure it out?
That issue's going to always be there. Yeah. Anytime you show up somebody that there was actually a better way that they missed, it is going to be a factor. No person likes to have egg on their face. Nobody likes to be embarrassed. So one of the things we're going to have to be very wary of is that very situation, and we have to be extremely tactful. It's not up to us to embarrass guys. We're not here to embarrass them. We're here to find answers. So I guess you're going to find choice words about a better future, successful answers, more likelihood of a good outcome. Your previous experiences have got you this far, which is great, but we can now take you further. Now we're going to find words like that because we don't want to embarrass guys. It isn't the point, because if they don't take improvements on, the company won't improve. And that means it's not just their job at risk, it's everybody else's job at risk as well. But we have to be recognising that it's a people process. In the end, it's all about people. This whole thing is about people, and we have to be respectful of that scenario.